Welcome, ladies and gentlemen, to this presentation entitled Measurement and Identification of Translational Stiffness Matrix for Static Loads in Machine Tools. This work is presented at the USPIN Virtual International Conference. My name is Nicholas Tyson, and I co-authored this work together with my colleagues Theodoros Laspas and Karol Sipka under the supervision of Andreas Akanti at KTH, the Royal Institute of Technology in Stockholm, Sweden. This presentation consists of 4 sections. The introduction section focuses on the importance of stiffness in machine tool design and operation, as stiffness directly affects the dimensional and geometric accuracy of machine parts. The main section is the methodology section. It presents a measurement and identification procedure for the full translational stiffness matrix at the tool center point of machine tools. The measurement procedure consists of inducing static loads at the tool center point of the machine tool using the loaded double ball bar and measuring the displacement with 3 linear variable differential transformers. The results and discussion section focuses on the application of the proposed procedure on a 5-axis machining center at KTH, as well as the quantification of the main components of the uncertainty budget related to the measurement procedure. The presentation ends with a summary of the proposed methodology. It outlines opportunities and limitations, as well as the next steps to be taken to support the machine tool design and process plan validation. Introduction. The stiffness of a mechanical system can be defined as its capacity to sustain loads which result in a change of its geometry. Its inverse is termed compliance. It is one of the main design criteria of machine tools as it affects their performance under load. High stiffness is important to precisely maintain the pose between the tool center point with respect to the workpiece during manufacturing. The stiffness at the tool center point is modeled using Hooke's law. Figure 1 visualizes this relationship in greater detail. It shows that the force vector is equal to the product of the Cartesian stiffness matrix and the deflections. There are a priori modeling approaches employing finite element analysis to support the design of machine tools, and a posteriori measurement approaches to validate the design. There are online approaches which identify the stiffness of a machine tool from features of machined workpieces, and there are offline experimental approaches. This work focuses on offline experimental approaches. ISO 200-30-1 provides guidelines for the measurement and evaluation of machine tool static compliance and hysteresis. The measurement consists of applying a quasi-static load between the spindle and the workpiece, or any machine component, and measuring displacements for each axis. The limitation of the process is the measurement of deflections solely in the direction of the applied force, ignoring possible cross-stiffness effects. Methodology. The measurement device and experimental setup are displayed in Figure 4. It comprises the instruments for the force loop and the metrology loop. The instruments for the force loop apply a static force between the tool center point and the machine tool table to induce deflections. The metrology loop, which is not subjected to forces, measures the deflections between the tool center point and the table, as well as the mount of the metrology loop on the table. The force loop comprises the loaded double ball bar as introduced in the framework of elastically linked systems, a tool adapter which consists of a steel sphere of radius of 50 mm attached to a steel shaft of a diameter of 25 mm with an overhang from the spindle of approximately 200 mm, as well as a set of table links. The measurement loop comprises a mounting structure holding 3 contact-type wireless linear variable differential transformer probes, equipped with flat-tip inserts. For the data acquisition, the wireless probes are connected to a data acquisition system, which is not in the picture. Figure 4 also omits the control system of the loaded double ball bar, which allows the control of the supplied air pressure. Let's take a look at the measurement procedure. The measurement procedure comprises 5 steps. The first one is the selection of a force vector. Then, locating of the table link in the machine-based coordinate system. The third step is the transformation identification of the probe's orientation. The fourth is the evaluation of the accuracy of the transformation. And the fifth is the measurement of the static deflections. These 5 steps are repeated for at least 3 linearly independent force vectors, which means that no one force vector can be written as a linear combination of the other force vectors. The first force vector shall be aligned coaxial to the z-axis of the machine-based coordinate system. This setup is shown in figure 4. The coaxiality with the z-axis facilitates the measurement of 3 linearly independent force vectors, and it leads to the maximum deflection in the direction of the z-axis, which is small compared to the deflections in the x and y-axis direction of the machine tool. That is due to the fact that the z-axis of the machine tool is usually the stiffest, as only small moments are induced into the structure. The location of the table links is probed using the machine tool's touch trigger probe to identify its center point. The probing and the machine tool's kinematic accuracy ensure a good orientation of the force vector along the z-axis in the machine-based coordinate system. The orientations of all force vectors are thus defined through the relative position of the steel spheres of the tool adapter and the table link. These 5 steps are repeated for at least 3 linearly independent force vectors. The next step is the calibration of the LVDT's output into the machine-based coordinate system. The process starts by positioning the tool adapter at a reference position in contact with the LVDT's planar tips, where the probe's output are set to 0. Then the unloaded TCP is positioned at different measuring points of 20, 30, 50, 100 and 150 micrometer along the X, Y and Z axes of the machine-based coordinate system, and the probe's output is recorded. The transformation matrix T that maps the LVDT's coordinate system into the machine-based coordinate system is calculated by solving the linear least squares problem. Disturbances in the measurement of the transformation can occur due to machine tool errors, form deviations of the sphere and probe tips, and measurement errors of the probes. These errors are assessed through 5 repeated measurements of controlled linear motions approaching the corner points of cubes with side length of 40, 60, 100, 200 and 300 micrometers centered around the reference position. Figure 8b shows the transformation error for the Cartesian components x, y and z as a function of the distance from the origin position. In the range of the measured deflections, the error of the transformation was less than 1 micrometer, which ensures a test uncertainty ratio of at least 5:1, as the maximum applicable load is 700 Newton and the stiffness in the z-axis is expected to be at most 125 Newton per micrometer. Once the transformation matrix is identified and acceptable, the loaded double ball bar is placed between the tool adapter and the table link. A predefined set of loads of 150, 300, 400, 600 and 750 Newton are applied incrementally. The TCP displacement is recorded by the LVDTs for each load level. The process is repeated 3 times for each axis of principal loading. The mean Cartesian deflections can be seen in figure 9. The small black line is the measurand while the thick lines highlight the associated uncertainty. Then, in the last step, the translational stiffness matrix is identified as the linearly square solution to the measured deflections and force vectors. The orientation and magnitude of the static force vector is defined through the load and orientation of the loaded double ball bar, and the vector of deflections is measured by the LVDTs. Results and discussion. The identified translational stiffness matrix can be seen in equation 1. The magnitudes of the components of the matrix are in accordance with the design requirements of the type of machine tool. The X and Y components are similar in magnitude, while the Z-axis is significantly stiffer. However, in theory the terms KYX and KXY, as well as KYZ and KZY, are considered to be equal in magnitude and direction. That is to say, the stiffness matrix is considered to be symmetric. In our case, they are not, and that is due to the fact that the stiffness matrix has been obtained by an unconstrained linearly squares formulation. Also, the magnitude of the components KXZ and KYZ are arguable, as the uncertainty for the deflections is significant compared to the measurand. The components of the uncertainty budget have been estimated by considering the following contributing factors. There's the LDBB load variation, which has been taken from a calibration sheet as a result of an in-house development. There is the transformation error, associated with the transformation of the measured deflections into the machine-based coordinate system. And as aforementioned, the error associated with this transformation has been assessed by 5 repeated measurements of controlled linear motions approaching the corner points of a cube centered around the reference position. Then, there is the tool adapter eccentricity. This component quantifies the difference in measured deflections for the same position of the tool adapter and table link due to indexed angular positions of the spindle using the S-pose command at different load levels. The spindle has been turned and then assessed by 5 repeated measurements at indexed angular spindle positions of 0, 90, 180, and 270 degrees. The component for the table leg eccentricity is similar. It quantifies the difference in measured deflections for the same position of the tool adapter and the table legs due to indexed angular loaded double ball bar positions at different load levels. The loaded double ball bar has been rotated in 5 repeated measurements about its own axis of rotation at indexed angular positions of 0, 120, and 240 degrees. The combined standard uncertainty is displayed in Table 1. Conclusion and outlook. This contribution proposed a measurement and identification procedure for the full translational static stiffness matrix of a machine tool using the loaded double ball bar instrument. As can be observed from the presented measurement results, the procedure is able to identify translational stiffness values in an efficient way. The immediate next steps are reducing the uncertainties associated with the measurement system, improving the procedure to identify quasi-static stiffness for a subset of the workspace, and to include one rotary axis contribution in the measurement and identification procedure. First works have been conducted at KTH on the identification of the quasi-static stiffness for a subset of the workspace. One measurement setup can be seen in video 1. The position-dependent stiffness can be used to support process planners to identify the stiffest areas in the machine tool. Figure 9 visualizes the magnitudes of the identified translational stiffness matrices in the workspace. This concludes the presentation. Thank you very much for your kind attention. This work has been supported by the Center for Design and Management of Manufacturing Systems at KTH.